We will find that Newton's second law is very powerful, and we will apply it to many different situations. In this video, we'll start with a basic scenario. Here is a procedure to follow when applying Newton's second law. Draw a force diagram of the system. Another common name for a force diagram is a free body diagram, and what we've called here the system refers to the object or collection of objects that are being analyzed. I can't emphasize enough how important it is to draw a force diagram. Make sure it includes the coordinate scheme and all of the force vectors acting on the system. Recall from the last video that a good technique to make sure that you've included all of the forces acting on the system is to consider objects that are in physical contact with the system and then include the force of gravity if applicable. Also, if you know the direction of the acceleration of the system, include that as well. Newton's second law relates net force and acceleration, so if you know the direction of the acceleration, that will also be the direction of the net force and useful information. Step 2 is to convert the vectors to Cartesian form. We need to do that so that we can do the next step, which is to apply the second law equation mathematically. Notice, like all vector equations, Newton's second law is multiple equations in one for each direction. By the way, I may have used a mathematical symbol here that you're not familiar with. This symbol is a Greek sigma that means to sum up the values. So here it means to sum up all of the force vector components in the x direction or in the y direction. It's equivalent to writing F net. Finally, check to make sure that your answer is reasonable. Okay, so let's try this procedure on a basic example. A man pushes a 60-kilogram block of ice on level ground with a force of 200 newtons at an angle of 15 degrees below the horizontal. If the friction between the ice and the ground, as well as the air resistance, are negligible, what is the acceleration of the block of ice? We'll use Newton's second law to solve this problem, so let's follow the procedure. The first step is to draw a force diagram of the system. The system is the block of ice because we want to find the acceleration of it. We can make sure we've included all of the forces acting on the block by considering what it is in physical contact with, and then add the force of gravity as well. The man is in physical contact with the block, so we can add that force to the picture. The floor is in contact with the block and pushes straight up with some unknown value, so we'll just label it force by the floor. So since we're neglecting friction and air resistance, then that's all of the contact forces, and then we can add in the force of gravity as well, which is also an unknown value. We'll actually learn how to calculate the value for the gravitational force in the next video, but we can solve this problem without knowing it. The other two things we should show on the diagram are the direction of acceleration, which we know is pointing in this direction because the ice can only slide horizontally on the ground, and the coordinate scheme as well. The next thing to do, according to the procedure, is to write the vectors in Cartesian form. We don't know what the values of the floor force and the gravitational force are, but we do know they're both in the y direction, so we can make their x component 0 at least. For the pushing force by the man, we can calculate its components with trig like this, which comes out to be 193 newtons in the x direction and 52 newtons in the y direction. Both of these components are negative because of the directions they point. And now we can apply the Newton's second law equation. Recall, we applied the equation in each direction separately, just like we did with the kinematic equations. Let's start with the x equation and solve it for the x component of the acceleration. And now we can plug in the values, which comes out to be negative 3.2 newtons per kilogram, or since a newton is a kilogram meter per second squared, the kilograms cancel, and then the units for the acceleration are just meters per second squared, which are the units that we would expect. So that's the x component. What about the y component of the acceleration? Applying Newton's second law in the y direction, we can solve it for the y component of the acceleration like this. However, in this problem, we don't know two of the force components in the y direction. So we appear to be stuck, but we actually already know that the y component of the acceleration is 0. We actually recognized this when we drew the acceleration vector in the diagram earlier. And so that means the final answer is 3.2 meters per second squared in the negative x direction. The last thing to do is to make sure the answer is reasonable. You may not know that 3.2 meters per second squared is a reasonable value, but we can at least recognize that the direction that it points in the negative x direction is reasonable. Well, that's it for this video. There are more applications of Newton's second law to come in the next few videos, but that's it for now.